Hi, welcome to lecture number 5 of this course on programming and data structures. If you recall the material that was covered in the last lecture, we talked about the formal definition of abstract data types. We talked about how to implement abstract data types in the C programming language. In particular, we looked at the abstract data type definitions of two common data structures. We looked at the list abstract data type and the array abstract data type. Just to recall what an abstract data type is, it's an abstract specification of a data type. It tells you what kind of data is represented in this data type and what kind of operations are associated with this data type. And all these are specified without alluding to any implementation details. We will revisit this formal definition in the first few slides of today's lecture and then quickly move on to looking at an implementation of the list abstract data type. And it will only be a partial implementation. We will only look at certain methods associated with the list abstract data type, and there will really not be an execution today, but we will look at the creation of the appropriate files associated with the implementation, and we will also look at the compilation process and what kind of files are created as a consequence of this compilation process. In the next lecture, we will complete the implementation of the list abstract data type and use the implementation in a programming exercise which will involve large integer arithmetic. So now let's move on to the slides. So the focus of today's lecture is the implementation of the list data type. Let's just recall what the list abstract data type consists of. The list abstract data type is used to model a sequence of positions storing arbitrary objects. Now the word arbitrary can be a bit misleading. You can assume that it's a sequence of positions storing objects of a certain data type. For example, you can have a list which stores integers. You can have a list which stores characters, a list that stores strings. You can also have a list that stores lists. Therefore, we really do not restrict the types of the objects. They can be as generic as you want to imagine. The most important thing with the list abstract data type is that the positions which are there in the list have a very well defined before and after relationship. That is, if you look at any pair of positions, there is a well defined before and after relationship between the two of them. The generic methods which we looked at during the last lecture are methods which return the size of the list, a method which returns a Boolean value depending on whether the list is empty or not. We have query methods which tells us whether a given position is the first position of the list or the last position of the list. Then we have accessor methods. The accessor methods return pointers to specific locations or specific positions in the list. For example, first and last are two methods which return pointers to the first element of the list and the last element of the list respectively. Before P and after P are methods which return pointers to the positions just before P and the positions just after P. Of course, if P is either the first position or the last position, before and after may not be well defined, and therefore the implementation of these accessor methods will have to take care of that. After all these methods, which are essentially structural queries about the list, we have update queries or update methods, where the methods that we have are the replace element method, which takes in as argument a position and a value and replaces the element in position P with a given value O. Similarly, we have swap elements, which takes as arguments two positions and exchanges the contents of the two of them, and insert before and insert after, which take a position and an object and inserts the element in a new position just after the given position P or just before the given position P. insert first and insert last, an object creates a new position and makes it the first position of the list or the last position of the list depending on the method. If you notice, all these are methods that increase the size of the list. The last method is one that can be used to shrink the list when necessary, remove a position. The method remove p removes a certain position along with the data item and maintains the list. The point to notice here is that after removing a certain position, the before and after relationship between different positions are well defined. These are all the details an implementation has to take care of. So what I have done is listed the different methods and specified to you what the input-output behavior of these methods are. And this is exactly the way any abstract data type is described. Without any implementational details, a specification of the data that is maintained in the data type, the basic types of those data, then the appropriate methods for creating the data, creating an instance of the data type, query methods, accessing the data structure kind of methods, and update methods. So the most important thing in the list data type when we look at the implementation is that we are going to create a data type called a position in the list, and the methods that are going to be associated with the list abstract data type will help us create the list itself by composing a sequence of positions. In other words, we are going to call these positions as nodes, and we are going to see that a list is obtained by composing a sequence of nodes in the correct order. Okay. Now, as you can see in the previous slide and in the last lecture, we have finished the design of the list abstract data type. Now we move on to implementing it. As we discussed in the previous lecture, what we are going to do is we are going to use features of the C programming language, and we are going to define them. We are going to define appropriate header files and appropriate files where the methods are implemented. Then for a programmer to use the data type, we are going to create an interface file, which is another header file, and then by including these interface header files, we will be able to use the abstract data type, which is described in types.h, and the appropriate access methods and the maintenance methods, which are defined in adt methods.c. This is the details of the implementation at a top level. So now we go to the program to see what the implementation of the list abstract data type looks like. And like I said before, today's lecture will not involve any execution. In particular, there will not be an executable, and we will not interact with that execution by giving inputs and getting outputs. What we will do is to create the abstract data type, compile it, and look at what is the kind of output that we have got and what it actually means. How to use it will be presented in the next lecture via an interesting programming exercise, which I will solve. Following that will be an equally challenging programming exercise that you will have to program and submit. So now we go to the program. So let us just look at the files that I have created. All of them start with the name list. So let me just list only those files. Let us just look at the files that we have. Okay. So as you can see, there are 5 different files here, right? And they're also named very carefully. So one is the list.h, right? And the file list.h consists of the type definition required to create the single node, the type definition associated with a single node in a list. The list methods.c is a file that consists of the implementation of the different methods associated with the list data type that we have defined. Then the list interface.h is a file that will be included by programmers who want to use the list data type. So in particular, the most important files that you will have to create when you create a new data type are the abstract data type methods.c, the abstract data type interface.h, and the data type.h itself. Right? And we will see further details of it by going to the files themselves. So let us just look at the file, the header file list.h. As you can see, there is, in this case, there is a type definition, right? And let us just look at the type that we have created. We have created a type called a container, right? We refer to this as struct container. This is the new data type that we have created. The data type struct container has two fields. One is of integer type. The other one is a pointer to struct container, and this pointer is given the name next. And for the ease of programming, we have given a new type name for struct container, and we call this the node type name, and this is done by using the type def keyword associated with the C programming language. And this is essentially what is there in the list.h. And as a generic principle, when you implement an abstract data type, whatever structures that you need to implement the associated methods can go into such a header file. Let me repeat, such a header file will not be included by the programmer who wants to use your data type. A programmer who wants to use your data type will only include the interface header file, as we will see next. So this is for the person implementing the details of the abstract data type. In particular, he or she specifies the different kinds of data associated with the data type. Okay. So here we have specified that each object in the list consists of one integer data item and a pointer to another object of the struct container data type. This is what we have specified here. Okay. So therefore we have specified the kind of data, and now you would want to know what are the different kinds of methods and how are they implemented. We've seen them, of course, in the slides. So let's take a look at the prototypes of the methods that are provided along with the implementation of this data type. Let us look at the methods. So this is in the interface file. Alright. So this interface.h, list interface.h, is created with all the function prototypes. And let me assert, these are function prototypes, and this is essentially the file that a programmer who wants to use your abstract data type, that he or she will look at. That is, if I want to use the list data type that we are implementing at the moment, then the file that I will look at to understand what are the function calls that I can make to access features of the list data type, I would look into this particular file. So let us just look at what this particular file consists of. Right? Remember that it's an interface file. First of all, we include list.h. Right? So we include the header file list.h, which consists of the definition of the node data type. Let us look at the different kinds of methods that we have. Right? So we have methods which return the size of the list, which returns a Boolean value, which is taken to be an integer, which is return value is considered to be of integer data type. The function is called isEmpty. The argument is a pointer to the node, pointer to a node. Similarly, isFirst and isLast are two methods, okay, that return a true value. This should of course have two arguments. The first argument is the pointer to the list itself, and the second argument is one specific location, and the query is whether it is the first or the last. Right? Therefore, there must be two arguments here. Then there are functions which return pointers on specific queries. Right? So let us just look at the function first as a representative example. It takes in as argument a pointer to a list where each element is a node, and then returns a pointer to the first element of the list. Similarly, the last function returns a pointer to the last element of the list. The before function also takes in two arguments. One is a pointer to the list itself and a pointer to a specific location, and queries whether the queries for a pointer to the location before the given location in the list. Similarly, the after function is a query for a pointer to the location just after the given location in the list. We will look at the implementations of these functions. Today we will not look at the update methods, we will look at them in the next lecture, but as you can see, the prototype definitions for the update methods are also here. There have been many requests on the forum for these programs. By the middle of next week, I will definitely put these programs up on Google Drive and ensure that these are accessible to every registrant in this course. And the same holds for the slides also. However, it is important for you not to directly use these programs and use these pieces of code and write your programs. It's important to write programs from scratch when you are a learner of the subject for the first time. However, they are made available to you so that you can read them and understand them at your leisure. Alright, so what is this particular file? This is an interface file, and let us recall the programmer who wants to use features of this particular data type implementation uses this interface file by including this file in his or her program. Right? And look at the most important thing here. The first thing that you include is the appropriate types that tell you what kind of data is manipulated by this particular data type. Right? That is what is included. Right? So we've taken a look at two very important files. Right? The first of these was for the person who's creating the data type. The second of these is for the person who's programming, who's using this particular data type's implementation in his or her program. That's the interface file. Now, the person who creates the data type itself also writes another C program in which all the appropriate methods are defined precisely with the appropriate return types. Remember that the header file consists of the interface.h file, consists of the function prototypes. This file, the list methods.c, consists of the implementations of the different methods which are in the interface file. And typically a programmer who wants to use the abstract data type will not look at the implementation in this C file. He or she will only use the interface file and program carefully. This is a good programming practice, and like I've asked in the last lecture, it's an exercise for you to find out what is this very popular programming approach. Okay, so now let's move to the list methods.c file. What you will see here is that all the structural functions, I mean those that do not update the data structure that we are setting up, all those methods are here, right? And each of these methods you will see is a very crisp and short piece of code, right? And that is how programming is made modular, right? So you break your programming exercise into small, quickly implementable functions and verifiable functions, and then put them all together carefully in a separate module. I repeat, a good programming practice is to understand the problem and break it down into small, quickly implementable functions whose correctness can be independently verified, and then you use these functions that you have implemented to create larger programs to solve other related programming exercises. Alright, so let us just look at the C file in which we have implemented all the access methods associated with the list data type. As you would have expected, we have included the file list.h. Now observe that we have separated into two files the data associated with the list data type, and in this file we only have the methods associated with the list data type. Right? This is a good programming practice. Nothing prevents you from putting in the contents of the list data type here too. Right? However, if your data type is very sophisticated and has many fields and so on and so forth, it's a good programming practice to put the data in a separate file and the methods in an associated file, the method implementation in an associated file, and like we have done, the interface functions, the prototypes of the interface functions in a third file. Okay, now here we have used the stdio.h and stdlib.h. Really, I think, though I have put in the stdlib.io.h, it is not necessary in this implementation as of now, but I will leave it there. So let us look at the first function. The first function, if you recall, was a function that returned the size of the list. Right? So let us just look at the function. Right? So the return value is very clear. The return value is an integer. Right? The name of the function is size. The argument to the size function is a pointer to node, and this pointer is called head. And let us understand how this function will be called, though we are not writing a program which is calling it. And this is the reason why in today's lecture we are not going to compile the program, get an executable and work with it. The motivation is to actually go through the implementation without making function calls and generating an executable. Right? So now let us just visualize how size is going to be called. The argument that size will be called with will be a pointer to the first element of the list. So let me repeat. So when you want to compute the size of a list, you call this function from whatever program you are writing. The argument to the size function is a pointer to the first element of the list whose size you want to query. Right? Now let us just look at this particular implementation. The implementation is a very crisp and short implementation. You will observe that it is a recursive implementation. We set up a variable called count. Count keeps track of how many locations are there in the list. And let me call this list head. Right? So head is a list. It is a list of nodes. Right? And we want to count the number of nodes which are in the list, which I am going to refer to as the head. Now, observe that this is a recursive function, as I just said. Count is an integer variable, right? It is initialized to 0. However, there is an additional keyword called static int. Right? This keyword is a C programming feature that keeps the value of count in previous function calls to the size function, and you can increment the value in every function call, or you can modify the value in every function call. After you return from a function call, the value of count will be appropriately modified. So in a way, you can think that there is actually just a single count variable for all the recursive function calls that we make to size. So let me repeat this. We have an integer variable called count. It is initialized to 0, so much is clear. However, there is an additional keyword called static. The word static means that whenever a function call to size is made, the previous value of count is retained for use in that particular function call. Of course, if it is a first function call to size, then count gets initialized to 0. Subsequent function calls to count will have the value that was subsequent function calls to count when the controller enters the function will have access to the value of count from the previous function calls. So let's look at this recursive function. Okay, so if head points to a null list, null is a keyword in the stdlib.h. It's a constant address. The meaning of null is that it does not point to anything. Okay? So if head does not point to anything, then you just return the value of count. Right? Remember that it's a recursive program. Right? So you enter this particular function call, you make a function call into size, you enter with a certain value head. If head is null, that is it does not point to anything, then you return the value count. Right? So let us just understand this. When the first function call is made, if head is null, that is it doesn't point to anything, observe that count is 0 and the value of count is returned correctly. If the list has like 20 elements, right, 20 positions, and you have finished, your head points to the 20th element, or the head points to the 20th element, at that time when the controller enters this particular function, count would have had the value 19, and head is not null because it points to the 20th element, so count gets incremented. Now observe that we make a function call here, right, calling size head pointer dot next. So if head is the last element of the list, head pointer dot next, we will ensure very carefully that head pointer dot next will be null. That is, we will mention that it does not point to anything. Right? In that case, it will be null. So this recursive call will then return the value of count. Right? All right. So tomorrow when we meet, we will look at an implementation, how we will look at a run by making a function call to this particular function, and we will see how the recursion actually works. Let's go to the next function. The next function basically is the isEmpty function, which takes as argument a position, right, in the list, right, and the isEmpty function takes a pointer to the list, right, and if it is null, it returns 1, saying that it is empty. Otherwise, it returns 0, saying that it is not empty. That is, if position is pointing to some element, then it will return a value 0, responding with the answer that the list is not empty. Okay. So the implementation for this is very straightforward. Right? If position is null, then position does not point to anything meaningful. So you just say that position points to an empty list and you return 1. Otherwise, right, if this condition is false, it means that the control does not evaluate this return 1. It comes here and returns 0, which means that position is not null, which means it points to something. Or rather, it points to a non-empty list. Okay. So the next query is to the isFirst function. The argument to the isFirst function is a list itself. Right? That is, we give a pointer to the first element of the list, otherwise the head of the list, and we have a pointer to a fixed position. Sorry, we have a pointer to some position in the list, and the query is that is position the first element of this list. Right? That is the query. So let us just look at this. It's very straightforward. When is position the first element of the list? If position and list point to the first element of the list, then position is the first element of the list. or rather position points to the first element of the list. Therefore, the check that you do is very simple. You check if list is equal to position, right, in value, that is, they point to the same thing, then you return 1, otherwise you return 0. Therefore, this is a single comparison, right? And if it succeeds, you return 1 saying that yes, position is the first element of the list, otherwise you return 0 saying that, well, position is not the first element of the list. So now we are given a position and a list and we are queried, and now we have implemented this piece of code to check if position is the last element of the list. Okay. Now let us just take a look at this. If indeed position is the last element of the list, then the position pointer dot next is null. Right? It should not be pointing to anything. Right? And therefore you return 1. So let us just understand this. Position is the last element of the list if position pointer dot next does not point to anything meaningful. In other words, position pointer dot next takes a value null. If not, if position pointer dot next is not null, then it means that there is a well-defined successor for position. Right? Let me repeat this. If position pointer dot next is not null, then it means that there is a well-defined successor for position, and we return the value 0. All right. So now let's look at functions, the whole class of functions that return a pointer, right, on specific queries. Right? Okay. So let us just look at the function called first, which takes as argument a pointer to the first element of a list, and we call that pointer itself list. Right? And we want the function to return a pointer to the first element of the list. Well, this is very easy. Therefore, you just return list itself, and one has to be very careful. One assumes that list points to the first element of the list. Right? Of course, if you want to misuse this function, you can misuse it, but it is not a very dangerous piece of code. So it's a very straightforward function. It returns the argument itself. There is an underlying assumption that when a programmer calls this function, he or she understands this function very precisely and passes a pointer to the first element of the list, and the return value is the first element of the list itself. The return value for the last element of a list, right? And how is the list given? The list is given by a pointer to the first element of the list. Now, what is the return value? The return value is a pointer to the last element of the list. How does one achieve this? We write this iterative function. Okay. So if list is null, then you return list itself. Okay. So this is a well-defined exit condition for function calls where list is, when the parameter which is passed, right, is null. Right? So then you return null itself. Otherwise, that is, if this function was not, if this statement was not executed, then control comes to the next statement, which is a while loop. Right? The next statement is a while loop, and let us look at the condition that is checked here. The condition that is checked here is to see if list pointer of dot next is not equal to null. Right? So this is an iteration where you can visualize this as the pointer moving right through from one location, from the head of the list all the way up to the tail of the list. Right? So if list pointer dot next is not null, then list is made to point to the next element in the list. Right? When do we exit from this particular while loop? When you are at a node, that is, when list is pointing to a node whose next pointer is pointing to null. Okay? In other words, when list is the list is pointing to the last element of the list. That is, you skip till the last node is reached, and here we return it. So what do we have so far? We have queries which return numeric values like size. Okay. Then we have queries that return Boolean values as to whether a list is empty or whether a certain position is the first element of a list and whether a certain position is the last element of a list. Then we have functions which return pointers to specific locations which are given in the list, that is the first element of the list, and returns pointers to the last element of the list. Now let us look at two functions, one which returns the predecessor of a position in a list and another which returns the successor of a position in the list. So this one returns a predecessor, the before function, and the after function returns a successor of a position inside a given list. So let's look at the arguments to the before function as an example. It takes as argument a pointer to the list itself, that is, it's a pointer to the first element of the list, and then it takes a candidate position. It takes a pointer to a candidate position. And it returns a pointer to the position which is before the given position. Of course, if the given position is the first element of the list, or if the list itself is empty, that is, the list is pointing to nothing, then you return null immediately, saying that, immediately responding with the answer that your query is meaningless. I cannot give you any meaningful pointer on this question. Right? So if list itself is empty, or if the given position is the first element of the list, then return null. Observe that we are using a method that we have already implemented in this particular file. Then you return null. Otherwise, you skip to the node whose successor is position. Okay? That is, you have a while loop where the condition that is checked is whether list pointer.next points to position. If not, you skip. In other words, list points to the next element. Keep repeating this iteration till list pointer.next is the given position. Right? At which point of time you return list, and that would be the element, that would be the position before your given position. Similar condition holds for the after function, which takes in a position in a list and returns a pointer to a node which occurs after this position in the list. Okay. Now let us look at the boundary conditions. If the list itself is empty, or if the position given is the last position in the list. Observe again that we are using a function that we have implemented in this file of methods associated with the list data type. Then you return the value null. Otherwise, you keep skipping till the list is the position itself. Right? So that is, you keep checking if list is same as the position. If not, then you skip. That is, you make list point to the next element in the list. When you come to look at the position, then you return the list pointer.next. That is, you will return the successor, the next element that list is pointing to. That is, return list pointer.next. Of course, you must worry about why is list pointer.next not null? Because if list pointer.next was null, then is list position, right, would have been true, is last in list position. That is the given position, the last element of the list would have been true. Therefore, this logical expression would have been true and you would have returned a null already. Because the control did not go through this particular if statement, it means that position is not the last element of the list, right? Nor is the list null. Therefore, you will return a pointer to a valid node in the list. That more or less brings us to the end of today's lecture. It is admittedly short. In tomorrow's lecture, we will look at the implementation of these methods which are used to update the list or modify the list, and this is how the data structure grows and shrinks. So therefore, the list that we will create will be the data structure which stores certain values, and we have the data structure that we have is an instance of the list abstract data type, and we have implemented some of the methods that are associated with this data type. When we meet in the next lecture, we will look at an implementation of the access, an implementation of the update methods associated with this list data type. There will be two programming exercises, one that I will show you in the next lecture, and another one where you will have to program essentially with minor modifications to the list data type, and both of them will definitely make you comfortable with programming with a list data type. So what would be in the next lecture? We will implement the methods associated with the updates of one list of the list data type or one list data structure, and we will use these methods in a interesting application, and the application will be a application to multiply large integers. So that brings us to the end of this lecture. I hope things were clear, and I look forward to your comments on the forum. Thank you.